In this video, we will review section 4.2, where we discuss the mean value theorem. When thinking about the mean value theorem, it's important to have a visual to just help us explain what's going on here. So consider our function f of x, and see that f of x we've considered endpoints a and b. So what the mean value theorem says is if you've got a function f of x that's continuous on a closed interval, in our case a to b, and differentiable on the interior of that interval, so the open interval a comma b, then what happens is whenever we've got this closed interval, we can look at the endpoints and we can draw a secant line between the endpoints. Now this secant line has a slope, and the way we would calculate the slope is the slope between 2 points, so the output value at b minus the output value at a, all divided by the distance between the input values b minus a. And what the mean value theorem tells us is that there exists some point c within this interval such that the slope of the tangent line through c, so the slope of this tangent line, actually is equal to the slope of the secant line between the endpoints of the interval. So by the mean value theorem, if this all is met, then we know that actually the slope between the endpoints must equal the slope at a certain point within the interval, which is the idea that these two lines are actually parallel. So that's just a visual that we want to think about as we go through the mean value theorem. And let's look at how we might apply this to some problems. So in some of our homework problems from this section, we're going to actually be given a specific function and a specific interval. Then we're going to be asked to show that the mean value theorem holds for this function in this interval. The main steps for doing a problem like that would be to first calculate the slope of the secant line that passes through the endpoints, that is f of b minus f of a over b minus a. This is going to be some value. Then calculate the derivative in general. Then finally, since in these problems we'd have to check that the conditions of the mean value theorem are met, is f continuous on this closed interval? Is it differentiable on the open interval? If so, once we've found this and we know the general derivative, then we would set the derivative that we found equal to the value that we found, which is the slope between the endpoints, and then we would just algebraically solve for x. This x that we find is the c that was promised by the MVT. Let's see this in one example. In this problem, we're asked to find the value or values of c that satisfy the equation, which is part of the conclusion of the mean value theorem. Now, if we want to apply and show that the mean value theorem would hold for this function over this interval, remember we first have to check two preconditions. So we'd want to mentally think through, is the function continuous on the closed interval? And, sorry about this, is it differentiable on the open interval? Okay, so is it continuous? Looking at the function, we see the only problem for continuity would be when the denominator of this equals zero, which would be at 0. But notice 0 is outside of our interval. So on this interval, the function is continuous. We need to think about the question, is it differentiable? Well, let's take the derivative and look at when this derivative would exist. So the derivative of this would be 1 minus x to the negative 2. One way you'd see that is, remember, rewrite this as x to the negative 1 and apply power rule for derivatives. So this could be rewritten as 1 minus 1 over x squared if preferred, and we see that this function exists for all values except where the denominator would be 0. So that would be at x equals 0. So while the derivative would not exist at x equals 0 not in our interval, so it is differentiable on our interval. So since the conditions of the mean value theorem have been met, we next start to apply this conclusion. So first we'd want to find the output values at both endpoints. So I calculated that here. The function value at 0.5 is 2.5. The function value at 2 is also 2.5. So then we would just find the slope between these 2 points by taking the output value minus the other output value. Okay, so we did 2.5 minus 2.5, all divided by 2 minus 0.5. Okay, top is 0, so overall this value is 0, but by the mean value theorem, we're told that that equals the value of the derivative at some point c. So our goal is to find what c makes the derivative equal to 0. We earlier found that the derivative of this function is 1 minus x to the negative 2. So we're going to say, when is that derivative equal to 0? And we know we're guaranteed there is some point within this interval that makes that true. So we might add an x to the negative 2 to both sides. X to the negative 2 equals 1. And we want to think this is the same as 1 over x squared equals 1. The only way 1 divided by something else equals 1 is if this entire term is also 1. So think, what when squared equals 1? Well, we would have x equals negative 1 and x equals 1. Both would yield x squared equaling to 1, which would send the whole fraction to 1. But we've got to think we're within this interval. So while both of these are a solution to the equation, we would just be looking at x equals 1 within the original interval of the problem. So the c value is at 1.